Good morning everyone. Very good morning बच्चों. Yes, I am very nice. Thank you Ritika. Thank you Kapil. Thank you Pratham. Yeah, today is our online class. Thank you beta. Okay, now today is very important topic we are going to discuss. Today we will discuss the nucleophilic substitution reactions. Nucleophilic substitution reaction. Simply we can say SN reaction. If you want to understand the nucleophilic substitution, first we will understand the substitution reaction. Substitution, what does it mean substitution? Simply you can say the replacement. Like I am giving you here the example. We have R bond L, the reactant. L is here our the leaving group. And plus G is any attacking reagent. It can be the electrophile or nucleophile. What is the substitution reaction? If L is substituted by Z simply, because L is the leaving group which will leave, so R bond G plus L. This is simply called the substitution reaction. They can be two types. You can see as here SN or SE. SN nucleophilic substitution reaction, SE electrophilic substitution reaction. So first case, if we are taking same reactant R bond L attacked by any nucleophile, the first nucleophile will attack in the presence of solvent. If leaving group is substituted by nucleophile, simple what will be the product? R bond Nu plus L minus. Why I am saying L minus? Because nucleophile will attack any electrophilic center, and this can be our polarity. This is our electrophilic center. Nucleophile will attack here, and this leaving group will leave. This is our leaving group. Leaving group here, leaving group leaves with bonding electrons. These bonding electrons are bonded. This property is called a leaving group ability. Leaving group ability, or we can also say a nucleofugality. Very important terms. So if leaving group leaves with bonding electrons, this reaction is called a nucleophilic substitution reaction. Because first nucleophile will attack to this electrophilic center, And in second case, same I am taking here R bond L, this is reactant, and this case electrophile will attack first. What electrophile needs? Nucleophilic center. Suppose that there is a polarity like minus and this is plus. Electrophile attack will to this nucleophilic center. So R bond electrophile. Leaving group is substituted by electrophile and this is our L plus. This is also leaving group, but here in this reaction leaving group leave without bonding electrons, because here L plus. So this reaction is called electrophilic substitution reaction. This property is also called a leaving group ability. This is also called leaving group ability. And we can say also this leaving group ability is electrofugality. So we will discuss this one reaction. We will focus to this our reaction, nucleophilic substitution reaction. Means L is our here leaving group, R bond L is our reactant attacked by any nucleophile, and leaving group substituted by nucleophile, R bond N will be the product, and L minus leaving group leave with bonding electrons. So we will study these reactions. Okay. Now types of SN reaction. Okay, no issue. The types of SN reaction. Types of SN reaction. Types of SN reaction, many types, like first types SN1, SN2, SN2H, SNI, SN prime, ERSN, SNNGP. ERN further divided into three types: ERSN1, ERSN2, and benzene mechanism. But today we are focused at SN1 or SN2 reactions. SN1. Today we will discuss about SN1 and SN2 reactions. Now, already we have the nucleophilic substitution reaction. Example I already gave: R bond L, nucleophile and reactant, and nucleophile will attack in the presence of solvent. and leaving group is substituted by nucleophile plus L minus. Leaving group leaves with bonding pair of electron. This is our substitution reactions. So first we are going to discuss about the SN1 and SN2. One side I am writing here the SN1 and second side SN2. Okay, this is about the general introduction. First we will do the general introduction, then we will understand each and every concept behind this. Okay, so SN1 called unimolecular nucleophilic substitution reaction. Why unimolecular? Everything we will discuss, I already told you. First I am writing here the general introduction part. SN2 bimolecular nucleophilic substitution reaction. Second point, two-step mechanism. Second point here in SN2, one-step mechanism, one-step concerted mechanism. Concerted means where bond formation and bond breaking takes place simultaneously. Okay, then we will see the mechanism. Two-step mechanism. Here's the first step. Same I am taking here the R bond L, the reactant. First it will ionize or dissociate. I am writing here the ionization step. Ionization means it will break into ions, R plus and L minus. And this is our slow step. We can say the RDS step. And second step, R plus attacked by nucleophile, and that will be our fast step, and product will be formed R bond N. Third one point here, one step concerted mechanism or transition state we can write also. Only one step. R bond L, same reactant I am taking here also. Attacked by nucleophile. But in this time, here is the polarity. Nucleophile will attack from back side. What does it mean? Nucleophile will attack from back side. We will discuss. Everything I already told you. So just write down. And this transition state will be formed. Nucleophile minus dot dot R dot dot L partial negative charge. This bond is being formed and this bond is being break. Finally, what will happen? This is also called transition state. what will happen? Nu bond R plus L minus. Third one, fourth one. Weak nucleophile required. Here, strong nucleophile. Why weak? Why strong? I already told you we are going to discuss each and everything. Weak nucleophile can be the generally neutral nucleophile. Like H2O, ROH, CS3, COOH, etc. A strong nucleophile generally anionic nucleophile, H minus, OH minus, CN minus, RCO minus, SH minus, OR minus, and neutral can be also, and neutral like NS3, RNS2, 1 degree amine, RNHR 2 degree amine, and PR3, etc. If you want to write the kinetics of reaction, 5 point kinetics of this reaction. So rate of SN1 reaction directly proportional to R bond L concentration. The concentration of R bond L की power 1. And we can say also here not depends the concentration of nucleophile. Fifth point here also in SN2 reaction. If you want to write down the kinetics of SN2, a rate of SN2 reactions directly proportional to, here only one step, so this is our RDS step because only one step. So what we can write here? R bond L concentration power 1 and also nucleophile concentration power 1. Now if you want to talk about leaving group ability, the rate of SN1 reaction directly proportional to leaving group ability. Obviously, if leaving group leave first, then rate of reaction will be also faster. Same with here. So leaving group ability, the rate of SN2 directly proportional to leaving group ability. If I am taking here the example R, I, R, Br, alkyl halide I am taking here, RCl, RF, and same example here RI, RBr, RCl, RF. So, what you can say? I already told you the leaving group ability. How we can compare this? तो R bond I greater than R bond Br greater than R bond Cl in no SN1 in RF, and same here, no SN2 also in RF. If you want to talk about the solvent, here is the polar, you can see, I will check first, I am writing here, then I will check polar protic solvent required, and here polar protic solvent required. Okay, I'm gonna check 1 second. Oh, it's okay, it's visible. 8 point. If leaving group attached with chiral carbon, then more than one stereo isomeric product will be formed, called mixture of enantiomers or racemic mixture. 1 second, I just want to check. Okay, little bit cut. Enantiomers, and I am writing here racemic mixture. Here also I am writing here, if leaving group attached with chiral carbon in SN2 mechanism, then only one product which will be called inverted product will be formed. Okay, 1 second, I will check your comments. बच्चों बस give me this class and you will understand each and everything about SN1 and SN2. Yeah, this is just the general introduction, so just wait. Okay, this is our general introduction. This is our SN1 and this is our SN2 reactions, general characteristics. Now please concentrate. 1 second. Now we are going to understand each and everything now. Okay, I am simply taking here the one example. CS3Cl plus NaH. In this example, we can see this is our nucleophile present, and that is our alkyl halide. So here we have also the electrophilic center like electrophile. So simply we can say this is our SN1 reaction for sure. Not SN1, this is our SN reaction. SN reaction we can say. Now what we are going to do? We are going to understand this is our SN1 or SN2. General introduction we did already. Now, if I am making here the alkyl halide 3D picture, so this is C, 1H, 2H, this is our base H and Cn. Tetrahedral geometry, and nucleophile wants to attack. This reaction is occurring. This will be this. Ab listen to me carefully. Bachcho, listen to me carefully first. Yeah, everyone. Yes. Very nice. Yes, bachcho. Yes. Yeah, we are taking this example CS3Cl and NaOH, and from this we are going to recognize that these reactions will follow the SN1 mechanism or SN2 mechanism. First, here's the carbon has 4 bonds. Since carbon has the 4 bonds, so why would nucleophile approach? First thing. Second thing, if no vacant orbital present, nucleophile will not approach also. Two very important things. So what to do? Is there any vacant orbital? Yeah, I am waiting. So I want to check your comments. Okay, 1 second. Yes. No. Yes, very right. Very nice. Here's the anti-bonding orbital of CCl bond, sigma star present. Very good answer. Yes, CCl bond has the bonding orbital also, and also vacant anti-bonding orbital. Now, you should have one more questions. Ki why, sir, you are suggesting? Yeah, you are choosing this vacant anti-bonding orbital of CCl bond. Here the 3 CH bonds, and they also have anti-bonding orbitals. Why you are not choosing the anti-bonding orbital of CH bonds? So listen to me carefully. According to the electron filling concept, electrons occupy the lowest energy orbital, and this anti-bonding orbital of CCl bond would have the lowest energy due to this electronegative atom, according to the Bent rule, because this electronegative atoms will surpass the orbital's energy and also the size. Yes, very important. So I am writing here the best approach for nucleophile attack is from backside. First I am writing this sentence, backside. Why backside? Because here is the polarity OH, if OH will attack from front side, then electron density of Cl is more electronegative, electron density more, will repel to this nucleophile. So best approach from opposite side, because less hindered position. So one I'm writing here, first reason, less hindered position, yeah, maximum away from large group. And second one, logically if we will see, then opposite side of CCl bond anti-bonding sigma star vacant orbital present. So this is our the reason. So what will happen if we are looking the mechanism? First observation, by first observation we can see this OH is the strong nucleophile. It can be the SN2. Second, because we already did the general introduction, and general introduction I told you there कि strong nucleophile required. Second, nucleophile will attack from backside, and this is happening in is here. Nucleophile is attacking from backside. So this is confirmed SN2 mechanism. This is SN2. So what is going on in SN2 mechanism? This OH minus is attacked to anti-bonding sigma star orbital, vacant orbital, C, H, this H, and this our Cl, polarity plus minus, and this is our anti-bonding orbital sigma star. We can write here the AVMO. This OH minus will attack from backside. What will happen? One step mechanism. Transition state will be formed. You can see this now. I am making general. This is the tetrahedral position. Like this. Like this. You can see this like this. I tilted a little bit there, and nucleophile is attacking this my hand side is the Cl and the all the 3H, and nucleophile is attacking from backside. So first what will happen? They will be like planar. And finally they invert it like the bird inverted umbrella. You can see this. I am making here the transition state first. C H and this OH minus taking here. This bond is being formed and this bond is being break. This here minus, that is our transition state. Or you can make also like this. This I am making the planar. Now C H. And now we want to talk about the geometry of this thing, this transition state. So it's looking like the pentavalent carbon transition state. So what is the hydration? Looking like trigonal bipyramidal, but not, because carbon don't have the vacant, don't have the d orbital. So it's simply the sp2. sp2, if we are writing here this sp2, then this we have here the p orbital, and this p orbital is attached by this OH minus, and also this C. This p orbital perpendicular to this plane. We can make here this also. OH minus, Cl minus. Nothing I did, just here is this plane and here is this plane horizontally. This transition state, and we can talk many more things about this thing, this transition state. This is sp2 hybridized, and this bond is 3-centered 4-electron banana bond. Finally, what will happen? The product C bond H and this is our H, this H, and backside from backside this OH minus will be attached. So this inverted product will be formed. We will see the stereochemistry in next topic, next turn. So first we are going to understand SN1 or SN2. So what I did here, I took one example, CH3Cl plus NaOH. Simply this is our SN reaction. It can be SN1 or SN2. So by first observation, because OH minus is the strong nucleophile, it can be the SN2. And second observation, attack is possible from backside, nucleophile attack is possible from backside. So SN2 mechanism confirmed. What does it mean? What I am trying to say? The SN2 mechanism requires the less hindered position for nucleophilic attack. This we understood. So many things we can write here. What we can write? Okay. Only one step mechanism, no carbocation formation, so no rearrangement, तीसरा, third one, pentavalent carbon transition state will be formed, will be involved. Fourth one, kinetics की बात करी जाए, we want to talk about the kinetics. The rate of SN2 reactions equals to K of SN2, we can write like this also, and there is only one step, and this step also called the RDS, the determining step. So R bond X या R bond L we can write, but here already we took the alkyl halide, so R bond X and nucleophilic concentration. Two molecule present, two molecule involved, so we can say the bimolecular and the concentration power is 1 and sum of the power of concentration is 2. That's why called second order reaction. 7. If we want to talk about isotopic effect, in this example CHHCl, if this H is replaced by D, isotope of H, then what will happen? What will happen in these reactions? The rate of reactions will be faster or slower. So observed already experimentally कि no effect. But if I took here, this is Cl35, and if I am replacing Cl35 from Cl37, this is the heavy isotope of chlorine, and this CCl bond is involved in RDS. So this effect is called element effect. Element effect. Element effect, yes, observed. So if I already took an example Cl35, if we replace Cl35 by Cl37, so what will happen? The rate of reaction will be slow because of the higher isotope or higher isotope bond strength increase. So bond strength increase, so we can say rate of reaction will be slow. Now many more things. Okay, you can write down everything. If we want to talk about energetics of SN2, or we can say energy diagram, or we can say potential energy diagram. So already we see the mechanism. If R bond L attacked by nucleophile and this nucleophile attack is from back side, here is the polarity. In the presence of solvent, and solvent is required, polar aprotic solvent. We will discuss each and everything. First, I am going to talk about the energetics or energy diagram. The transition state will be formed, NU, this bond being formed and this bond being break. This is called our transition state. Finally, NU bond R will be formed and L minus will leave. So you want to draw or the energetics. So simply SN reactions are the exothermic reactions. Here we are taking the potential energy or energy, and here progress of reaction. Or reaction coordinates. This is our reactant energy, and here is our product energy. Only one transition state is formed, so this graph will be like this, and this is our transition state first. So reactant, and this is our product. And delta H heat of formation equals to enthalpy of product minus enthalpy of reactant. Okay, now this is all about the SN2. And now we will take one more example. One more example. Suppose that this alkyl halide atom CS3 Cl and any nucleophile, we took any nucleophile. Think about what about the sigma star anti-bonding orbital of CCl bond. Think about sigma star. That is our sigma star anti-bonding. Nucleophile cannot attack from backside. Why? Because of the steric crowding. Big bulky group present here. So what will happen? First observation, what this can be the SN because nucleophile cannot attack from backside. Second observation, here's the bulky group CS3, and Cl. Now this CCl bond dissociation easily here or in this example, suppose that we took previous example H is this CCl bond and this CCl bond. This Cl has the good leaving tendency or this Cl has the good leaving tendency. You can easily say, sir, because of the steric hindrance, because of the plus I effect, here this Cl will dissociate first. Yes, this Cl is dissociate first. So what I am writing here, it gets easily dissociated or leaving tendency of Cl even before attack of nucleophile. So what it represents? The SN1 mechanism. Easily dissociated because of bulky groups, steric hindrance. So if you want to see the mechanism of SN1, so we have this example. In SN1, it's confirmed that it's a SN1 mechanism. This reaction will follow the SN1 mechanism. In SN1 mechanism, already we know the two step and first step, the ionization step, C bond CS3, 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 Cl. First step, ionization or dissociation. What will happen? C bond CS3, CS3, planar carbocation will be formed, plus Cl minus. And in second step, that will be our slow step, also called RDS, already we checked. Second step, this is our planar carbocation. Has the perpendicular vacant p orbital. Nucleophile attack can both side, on front side also and also from back side. So two product will be formed. One product will be called, if same side, the retained product, and from back side the inverted product. C bond CS3, bond CS3, CS3 bond nucleophile. So this is a retained product. And another C bond CS3 NU CH3, CH3 inverted product. From here, what we can see, SN1 mechanism wants bulky groups. It requires crowding. So point we can write here, which we understood. First, two-step mechanism. Second, carbocation intermediates. Will be formed. Third, rearrangement possible. Fourth, kinetics. If you want to talk about kinetics, the rate of reaction directly proportional to equals to K of SN1, constant of SN1, and concentration of R bond X per 1. Fifth, that's why called unimolecular, because one molecule is involved here. And six, first order. First order is the bookie's language, but in nice books you can find the pseudo first order. Pseudo first order. Very important. Why pseudo first order? Because here this is the alkyl, it's an alkyl halide, and because of the bulky group, this CCl bond has not broken. This CCl bond has not broken, only becoming weak. I am writing here. It's an alkyl halide. This CCl bond has not broken, but becoming weak because of the bulky group. Bond has not broken, only bond become weak, becoming weak. What does it mean, sir? It means कि for ion formation there is polar solvent required. We already know this. The note, we can write a note. For ion formation, polar solvent is required. What does that mean? So here in SN1, polar solvent will be there, polar solvent, and already I told you in a general introduction, the polar solvent required. If here is the polar solvent also present, then the rate of reaction we can write rate of SN1 reactions equals to constant of SN1 R bond X alkyl halide concentration and also the concentration of solvent, because two things involved here, alkyl halide and solvent. But here the solvent has a large amount. So large amount, the concentration of solvent will be fixed, and this fixed concentration we can assume in this constant. So finally, what we can write the rate of the SN1 reaction equals to K of SN1 R bond X. That's why we are saying the pseudo first order. This is very important. Pseudo first order. If we want to talk about isotopic effect, no, not present experimentally. 8. If we want to talk about element effect, yes, I already told you in a SN2 mechanism. Now, more points. Okay. Energetics of SN1. General mechanism we already know. R bond L, this is the polarity attacked by nucleophile, and nucleophile attacked from backside. What will happen in first step? No. SN1, not from backside. R bond L, there is a two step. First step is ionization. R dot L. This bond start breaking. This is the first transition state 1, and finally this bond will break, R plus L minus, and in second step R plus attacked by nucleophile. The first step, what will happen? This bond start formed. Finally, what will happen? R bond N will be formed. So transition state 2 will be formed. If you want to draw the graph between energy versus progress of reaction, or we can say reaction coordinates. Already we are assuming generally SN reaction are the exothermic reaction. So here we can take the reactant energy, and here we can take the product energy. Now the graph will be like this. This is the transition, state 1. This is the transition, state 2. And this is the carbocation formation, R plus. R plus formation. That is our E1, EA1 we can write. Here E2, EA2. So you can see here, I took here the EA1 greater than EA2. Why? Because here the first step is slow step, and slow step required the more energy. That's why I took EA1 greater than EA2. And enthalpy of formation, simply we can write here also say enthalpy of product minus enthalpy of reactant product. Now this one. Now if we now we understand what is the SN1 reaction, what is the SN2 reaction. SN1 required more crowding, SN2 required less crowding. In SN2, nucleophile will attack from backside. In SN1, before nucleophile attack, it gets easily dissociated. This is all about SN1 and SN2. Now I have a questions for you. Yes. Which reactions will be faster, SN1 or SN2? Yeah, I will check your comments. Tell me. Okay, I will drink the water a little. 1 second. Okay, now tell me. Yeah, Pratibha. Yes. Which one is faster, SN1 or SN2? SN1 is faster than SN2. If we want to understand about the rate, then what we will go through by RDS of SN1 and RDS of SN2. And in RDS of SN1, leaving group leaves before nucleophile attack. Whenever RDS of SN2, leaving group leaves by the help of nucleophile attack. Yeah, not opposite. Listen to me carefully. It's all about SN1 or SN2. If we want to understand more about SN1 and SN2, the factor affecting factor affecting SN reaction, या SN1 and SN2 reaction. First, nature of substrate. Second, nature of leaving group. Third, nature of nucleophile. Fourth, nature of solvent. First we look general SN1 and SN2 reactions. We want to understand each and everything about SN1 and SN2 reaction, then we should know about nature of substrate, nature of leaving group, nature of nucleophile, nature of solvent. If we will study these four things, we will completely understand about SN1 or SN2. A little bit nature about nature of substrate. We understood कि in SN1 we want a bulky alkyl halide, and SN2 we want less hindered position. So simply, first write down a heading: nature of substrate. Nature of substrate. These are questions. Compare the rate of reaction SN2 in following compound. By this example you can understand about nature of substrate. First example, C bond H, HCl, nucleophile is attacking. दूसरा second one, C1 CS3, bond H, bond Cl, any nucleophile is attacking also here. These are the substrate, these are the alkyl halide I am taking here. Third one, nucleophile, any nucleophile, CS3, HCl. Fourth one, CS3, Cl. Fifth one, C, H, Cl, CHO. These are the 5 alkyl substrate I took here. We can have only the one variable. Here I took the different substrate. Nucleophile are the same here. So we want to talk about the rate of reaction of SN2. If you want to talk about the rate of reaction of SN2, what we are doing here? This nucleophile is attacking from back side to the anti-bonding sigma star vacant orbital. Vacant orbital. So I'm writing here some things how we can compare. First things, how we can recognize SN2 reactions preferred less hindered positions. So first, less hindered position. Second, by transition state also we can understand very clearly the rate of reactions. So transition state, yeah, stability of transition state, or simplify, you can write like a reactivity of SN2 inversely proportional to crowding on carbon of leaving group. First, or reactivity of SN2 directly proportional to electron deficiency on carbon. I will check. This all have the polarity plus minus plus minus. This nucleophile want to attack here, so we can write also electron deficiency on carbon. About transition state we can write also reactivity of SN2 directly proportional to stability of transition state. More stable the transition state, reaction will be more faster. So these are our the observation. By this first crowding on carbon we can give easily the answer, but we are going to understand this concept by transition state, so you can clearly give the answer. So I am first making the transition state. Now first transition state. This H, C, H, H. This is our P orbital, and this is our nucleophile minus, and this is our Cl minus. This is first transition state. If we want to understand the general observation of this transition state, then what we can say? This nucleophile has the partial anionic character, and also this chlorine has the partial anionic character. So this completely transition state has the anionic character. Anionic character. Okay. Now this is the first transition state. I am going to make the second transition state. Here one CS3 group, H, and that is our pure vital. This is nucleophile minus, and this is Cl minus. This is our second transition state. What is going on? This transition state has the anionic character, and this CS3 group means plus I group, not plus H, because plus H wants vacant p orbital, and here is not vacant p orbital, so only plus I. Plus I destabilize the transition state. It's become more anionic because it's the electron donating group, plus I. So what is going on? If crowding is increases, transition state become unstabilized, so rate of reactions decreases. This understand? That's why I took here the example of electron withdrawing group, CHO. You can see, that's why here I increase 1 CS3, 2 CS3, 3 CS3. So I am going to make the fifth transition state of this group. What is happening? C, H, 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 C, C, O, H. Here is our p orbital. This is our nucleophile. This is our Cl minus, and here also this is pi bond, C bond, C double bond, parallel overlapping. Here is the pi bond. And they can also, this pi electron density also delocalize with transition state p orbital. This. So a type of minus I or minus R can be stabilize the transition state. So what we understood from here? We understood from here K, if EDZ increasing, the rate of SN2 decreases. If EWZ increases, then rate of SN2 increases. Here we can check the 5 example, and we want to give the order. So first of all, CS2Cl, CHO. This is the fifth one. After that, the first one, CS3, Cl, and CS2, Cl, CS3, Clear? CH, CS3, Cl. After that CS3, CS3, CS3 here, Cl. So what will be the order? Here is the Ne can be the Ne, E, WG group. Increase the rate of reaction. Even already checked, experimentally we can say, or already we checked in 3-degree alkyl halide, no SN2. So from here we can see the SN2 reaction mechanism. Okay, now I will give the another example to compare the rate of reactions of SN1. From that thing we will understand the nature of substrate for SN1 mechanism. Compare the rate of reaction of SN1 in following compounds. First example, second example, third example, fourth example, fifth example, any nucleophile want to attack. So what is going on in SN1 mechanism? First, ionization. Ionization, what will happen? This is here you can see if this Cl will leave, here the carbocation will form and it will resonate by this lone pair of electron. So what we can write, MEO double bond plus CH2 like this. So little bit already we know कि SN1 prefer more crowding in order they can get easily dissociated. So By observation, what we can say here? We can say rate of reaction. We can write here a note. A rate of SN1 reaction directly proportional to stability of carbocation in first step. But it is not so true, because the right thing is here we can write rate of SN1 reaction is directly proportional to ease of dissociation. Yeah, we can write here, this is the right. Higher the dissociation, higher will be the rate. Or we can write also that dissociation dominates over stability of carbocation. Sorry. So by these things we can give directly the order. Order you can write directly. If I am taking this thing, example number first, example number second, example number third, example number 4, example number 5. So what is going here? Steric crowding here is more, steric crowding less, little more less, more. Even this carbocation is not found practically. And here what is going on? We can make this thing C, H, Cl, and here the OMe. If this is the CH less steric crowding, so want to attack the sigma star anti-bonding orbital, and this lone pair of O will go to this anti-bonding vacant orbital, and this Cl will leave. Like you can say कि घर का बंदा जब लात मारेगा तो पता भी नहीं चलेगा. Such reaction is called, here we can write SNNGP. So carbocation formation will be easy. You can see, because leaving group leave by the help of this resonance. SNNGP, never group participation. So what can we can write the order? What can be the order? First CS2Cl onto CS3. This is our EDG group. Increase the rate of reactions. Then first CS3, CS3, Cl. Then second, then experimentally already check in 1 degree and methyl halide chloride, no SN1. So here you can see the rate of reaction directly proportional to if EDZ increasing, rate of SN1 decreases if EWZ increases. We can write like this. Now, what we learn from here? SN1 and SN2, 3 degree, 2 degree, 1 degree, and methyl halide. Three degree halide, alkyl halide we are talking here. So we observe this कि SN1 3 degree will give, 1 degree will not give, CS3 will not give, and SN2 CS3X will give, 1 degree will give, and 3 degree will not give. So we have no confusion about this. 3 degree alkyl halide will give this SN1 or alkyl halide, or we can say R-bond-L type system, where L is the leaving group. It can be alkyl halide or other compound, and 1 degree no SN1, methyl halide no SN1, SN2 3 degree no SN2. So question will ask from 2 degree. Now I will give the one example, and already you can understand the note about which we wrote before. Okay, ease of dissociation dominates over stability of carbocation. Like I am giving the example simple. Compare the rate of reaction and following compound. Sorry. We have two compounds. One is and second is these are the two compounds, A and B. Simply you can check in both points. We want to talk the stability of carbocation and also the rate of reaction for SN1. So here's the carbocation. This is carbocation, and here the carbocation. If we want to talk about the stability of carbocation, then simply we can say degree are same when we will check by hyperconjugation. hyperconjugation more, less alpha H more, alpha H less. So stability of carbocation this. But if you want to talk about rate of reactions, that will be reverse because of steric crowd.